Friends, I'm Ms. Rajisha from Gokulam Public School. Today we are going to discuss about the chemical and physical properties of halogenoalkanes. Okay, so first let us see the physical properties of halogenoalkane and halogenoarine. Let us first discuss about the boiling point. Okay. So, if you compare the corresponding halogenoalkane and hydrocarbon, the boiling point of halogenoalkane will be higher than the corresponding hydrocarbon. For example, if you are comparing CH4 and CH3Cl, CH3Cl must have the higher boiling point than CH4. Okay. Reason for that is actually in hydrocarbon there is only one type of intermolecular force present. In hydrocarbon there is only one type of intermolecular force present. That intermolecular force is only van der Waals force of attraction. But in halogenoalkane we know that the CCl bond is polar. Okay, the bond between carbon and chlorine, that is polar. So because of that, because this is highly electronegative and this is less electronegative, so delta plus and delta, the electron will be, the shared pair of electron will be moving more towards chlorines, right? So this is polar. Because of that, there are two type of intermolecular force of attraction. One is van der Waals force of attraction and the other one is dipole-dipole interaction. So since there are higher intermolecular force of attraction between the halogenoalkane, the boiling point will be higher for halogenoalkane compared to the corresponding hydrocarbon. Okay. Now let us see the next slide. Next. Now, as the size of halogenoalkane increases, the attraction also increases, so boiling point increases. So what will happen? As the size of halogenoalkane increases, the van der Waals force of attraction also increases, okay? Because the number of electrons is increasing. So what will happen? The boiling point also increases. And as the size of the alkyl part increases, means two type increase may happen, right? Maybe CH3Cl, CH3CH2Cl, CH3CH2CH2Cl, like that. If the alkyl part is increasing, then also the boiling point increases because of increase in the intermolecular force of attraction. And if the size of that is the halogen is changing, if the alkyl group is same and the halogen is changing, so what will happen? Depending upon where which is having more size here, fluorine, chlorine, bromine, and iodine, we have to see. Fluorine is having smallest size and iodine is having a big size and big molecular mass, right? So this must have more boiling point. Okay, the alkyl group which is connected with the iodine must have more boiling point compared to the other halogenoalkane because it is having more size and more mass, molar mass. Okay. Okay, now let us see the next case. For isomeric halogenoalkane, the boiling point increases with the branches. Let us see this case. This is isomer. All of these are isomer. But what is the difference? The bromine atom is attached on in the straight line carbon chain. The bromine atom is attached at one end. And here the bromine atom is attached into the second carbon atom. Here the branching is different, right? So the bromine atom is attached to this second carbon with one CH3 branch. Okay. So as the branching increases, what will happen? The area of contact with the other molecule will decrease, right? Here, everywhere there is no hindrance. Everywhere area of contact will be there. But if you are moving from this side to this side, the area of contact will decrease. Okay, the area of contact will decrease if we are moving from this side to this, so that the intermolecular force of attraction also will decrease from this side to this side. That is the reason. Okay, so as the intermolecular force of attraction decreases, the boiling point also will decrease. That is the reason why the straight line is having higher boiling point than the other. Okay. Now, if you look at any group of halogenoalkane with a different alkyl chain, you can see the first members will be gases, and the still higher members become solid, still higher members become, still higher members become solids. Okay, and here if you see this halogenol, the red color indicate chlorides. So the chlorides are lighter than bromides. Okay, bromides are lighter than iodides, right? So which is having less boiling point, the chlorides must have less boiling point than bromides, which in turn have less boiling point than iodides. Okay, and all set of halogenoalkane we can see this difference. Okay, now para isomer having higher melting point than meta isomer. If you see the para isomer, see if you are keeping it in a shelf or somewhere, it is having a nice geometry so that it will easily arrange, right? So because of that, because of this particular shape, the symmetry of para isomer fits the crystal better. That is the reason why para isomer is having a high melting point than the meta isomer. Okay, so now next thing is, if you look at the density, what will happen as the molecular mass increases, the density also will be increasing. Bromo, iodo, and polychloro derivatives of hydrocarbon are heavier than water. They are heavier than water. Bromo, iodo, and polychloro, more than one chlorine atom are there in the alkyl halide, then they will be heavier than water. The density increases with increase in the number of carbon atom and also the halogen atom and the atomic mass of halogen. If the atomic mass of halogen atom is increasing, also density will increase. Okay, so next, solubility of halogenoalkane in water. So it is less soluble in water. There is a reason for that, why this is less soluble in water. Okay, energy is required to overcome the attraction between haloalkane molecule, right? So if you are taking haloalkane, if you are taking water, this is water, and we are going to add haloalkane into this, right? This is haloalkane. So in if you are haloalkane is inside a vessel, means there will be attraction between the haloalkane, right? There will be attraction between haloalkane here. There will be attraction between water molecule here. Okay. So these two type of attraction should be there already. So the energy is required to overcome the attraction between haloalkane molecule and break the hydrogen bond between water molecule. Okay. So we need to break, in order to mix water with the haloalkane, we have to break this bond. At the same time, we have to break this bond also. Okay. So less energy is released when new attraction occurs. So suppose hydrogen, this haloalkane and water is forming a bond, intermolecular force, okay, of attraction is there, is set up between the haloalkane and water. It is not releasing much energy to break these two bonds. Okay, if that is releasing much energy to break these two bonds, then only the haloalkane can dissolve in water. Okay, then only. Clear? Now next is solubility in organic liquid. So in organic solvent, it is soluble because the new intermolecular attraction between haloalkane and solvent molecule have much same strength. That is the reason, their strength. So both of them is having the same strength so that they will dissolve. Haloalkane will be dissolving, halogenoalkane will be dissolving in any organic solvent. Okay. In detail, how we can discuss it. This is an organic solvent. Okay, AA. This is halogenoalkane, BB. So when you are setting up a bond between, intermolecular attraction will come between A and B, that is having the same strength as BB and AA. So it can dissolve inside this solvent. Okay, organic solvent. Okay. Now let us see the next. Reaction of haloalkanes. We are going to discuss about the reaction of haloalkane. There are three types of reaction In the slide, we are not going to discuss all. We are going to discuss now nucleophilic substitution reaction. Okay. So let us see the nucleophilic substitution reaction at first. So first we have to understand what is a nucleophile. Nucleophile means it is an electron-rich species and which is seeking for a positive center. Okay, nucleophile opposite you have to think electron-rich it is. Electrophile means nucleophile means nucleus loving, that is positively charged love. So it is seeking for a positive center. It is electron-rich and it is seeking for a positive center. Okay. The substitution reaction here is initiated by nucleophile. That is the reason why it is called a nucleophilic substitution reaction. So these are the example for some neutral nucleophile and charged nucleophile. Cl minus, I minus, M minus, F minus, NH2 minus. And these are the neutral nucleophile, but it is electron rich because they consist of a lone pair of electron. We have learned this, right? In grade 11 already learned water consists of two pair of two lone pair. Nitrogen has one lone pair, here also lone pair. Since it is having an excess pair of electron, it is electron rich. So these all will act as a nucleophile. Okay. Now, what is ambident nucleophile? Very important thing. Ambident nucleophile means if it is it has two point, for example, cyanide group. If you are taking, it's a hybrid of two contributing structures and therefore can act as a nucleophile in two different ways. CN is a cyanide, right? So if you are taking CN, actually the CN can bond with this carbon during substitution reaction, or nitrogen also can bond. Okay, so it has the capacity to bond with nitrogen and carbon. So two centers are available in two nucleophiles are available. Nucleophilic centers are available here. So that is why it is called an ambident nucleophile. Can we see another example? Another example for this is NO2. In the case of NO2 also, actually oxygen also will be bonding with the alkyl group. Also this nitrogen is having a lone pair of electrons, so it can also bond with the alkyl group. So since there are two centers, nitrogen and oxygen, if it is bonding through oxygen, then it is called a alkyl nitrite. If it is bonding through nitrogen, then it is called a nitroalkane. That is the difference. Okay, so you will get two different names. And same for ambident nucleophile like Cn minus also the same thing. Cn, if Cn is bonded through nitrogen, then it is called a alkyl isocyanide. If it is bonded to carbon, then it is called a alkyl cyanide. Okay, that is the difference. So two different type of nucleophilic center we can see here. Okay. Now next is nucleophilic substitution reaction. How the nucleophilic substitution reaction is taking place. First, the nucleophile will approach the alkyl halide. Okay. First, what will happen? The nucleophile will be approaching the alkyl halide. When the nucleophile approach the alkyl halide, you can see the charge separation is already there. Carbon is having a positive charge and halogen is having a negative charge. Okay. So this nucleophile will be seeking a positive center. So a positive center is available here, right? A positive center is there. So nucleophile will be attacking all these positive center, and this will leave because pi bonds are not possible on carbon. So the nucleophile will be attacking on the carbon and it will form a new molecule, and at the same time X will be acting as the leaving group that will leave. Okay, that is nucleophilic substitution reaction. Okay. And let us see some of the reaction, nucleophilic substitution reaction. So here we can see different reagents are using here. And if you use NaOH, OH minus will be the nucleophile. So when Rx, okay, RCl, when it is reacting with our nucleophile, NaOH is there, but OH minus will be acting. So what will happen? This OH, okay, we can take one example, CH3 CH2Cl. Okay, so what will happen here is between this C and Cl, that means CH3 CH2 Cl, between the C and Cl, this is delta plus and delta minus. So OH minus will be approaching here and attack over here, and the Cl minus will leave. So that we will get corresponding what CH3, CH2, OH we will be getting, and HCl formation will be there. Okay. Sorry, NaCl here, sodium is there, NaCl formation would be there. So this will result in the formation of ROH. If water is there, the same reaction, OH minus is again coming here, and the same reaction will happen, and we will get ROH. So if NaOR is there, it will be split into Na plus and OR minus. So OR minus will be our nucleophile. Since OR minus is a nucleophile, minus is on oxygen, okay? OR minus is the nucleophile. What will happen? CH3, CH2, Cl will move, in place of that OR will come. That's all. Okay. In this way, we will get ROR dash. We will get a product. If sodium iodide is there, what will I minus will be acting? So what will happen? CH3, CH2 in place of the halogenoalkane. Who will come? Iodine, halogen, iodine will come. Okay. This is what happening here. And now, next is reaction with the NH3. So, in the case of NH3, how the reaction will be taking place? So, CH3, CH2, Cl, when react with the NH3, actually what is happening here, let us see. This NH3 I am writing here, HNH2 we can write, okay? So this H and Cl will move and they will bond together. So we will get CH3, CH2, NH2. Do you understand this? I am writing it again. That is CH3, CH2, Cl is our halogenoalkane that is reacting with NH3. So we will write NH3 like this. Okay. So here what is H and Cl will remove. And then we will get the product CH3, CH2, NH2. That is what here RNH2 is written. Primary amine we are going to get. If RNH2, so ammonia is reacting, we'll get primary amine. If RNH2 is reacting, this is primary amine. So CH3, CH2, Cl, when react with the RNH2, we can write like this, H, RNH, like that we can write. And this H will be reacting with the Cl and it will remove HCl and we will get CH3, CH2, R, NH2, NH. One R will come here, RNH. Okay, that is why we are getting RNH R dash here. RNH R dash. This will be R dash. Okay, so next reaction is reaction with the R dash NH. Okay, this R dash NH is reacting with the again CH3, CH2, Cl. Suppose here also this HCl will be reacting. Okay, so we will be getting CH3, CH2, N, R dash. Understand? In this way, we will get the product. If it is reacting with the KCN, CN should be there. Okay. So if it is reacting with the KCN, K plus and CN minus is there. CN minus will be coming and reacting, and RCl will react with the CN minus, and what we will get is the Cl will be substituted by the Cn, so we will get RCn. Okay. Another example, AgCN. AgCN, it will be bonding through nitrogen atom through this lone pair. So AgCN, when reacting with the RCl, we will get R. The Cl will be substituted by NC. Okay. And isocyanide we will be getting here. Okay. Now, if KNO2 is reacting, we know that NO2, there are two nucleophilic center here. Actually, nitrogen is having a lone pair that will act as, that will also bond, and this oxygen also bond. Okay, so if you take the KNO2, it is ionic, right? So it will be bonding through the oxygen atom. Okay, so we will get the product R. The Cl will be substituted by ON double bond O. Okay, alkyl nitrite we will be getting. So if an covalent compound AgNO2 is reacting with the RCl, what will happen? Not the oxygen, it will be bonded with the, substituted with the, Cl will go and in place nitrogen will come, double bond or double bond will come. Okay, so that is, we will get a nitroalkyl in the case of AgNO2. Okay, in the same way, RCO Ag when react, the nucleophile will be RCO minus. So if RCl is our halogenoalkane, it will be reacting with the RCOO minus, right? So the Cl will be substituted with that. So we'll get RCOO R. Clear? In this way we will get. Now next is lithium aluminum hydride. So the nucleophile will be hydrogen over there. So we will get RCl will be substituted with the hydrogen. Okay. So we will get the product RH. Okay. So now next is, if you are taking R dash M plus, okay, here R dash will be negative, that will be our nucleophile. So RCl when react with the R dash, the Cl will move and R dash will come and attack. So we will get R dash. Clear? Like this we will get. So these all are the different reactions. So but here we can see the different atoms are joining here with the alkyl group. If you're taking KCN, R will be, okay. If you're taking AgCN, R will be joining with the nitrogen, right? Here if you're taking KCN, R will be joining with the carbon atom. And this, of course, the CN we learned that is ambident nucleophile. And what should be the reason behind that? That is also important. Why different molecules are bonded with the different? The answer for that is here. Okay, KCN is what? KCN will already know that it is ionic in nature. Okay. And since it is ionic, what will happen? It will undergo ionization in solution and we will get Ka plus and Cn minus ion. Okay, cyanide ion. Now, both the carbon atom and nitrogen atom, we know that it has a capacity to act as nucleophile, but the attack take place mainly through carbon atom and not through nitrogen atom, because the carbon-carbon bond is more stable than carbon-nitrogen bond. Okay, because the carbon-carbon bond is more stable than carbon-nitrogen bond, because when this is formed, it will be reacting with the CH3, CH2Cl, right? So the Cl will go and Cn will come. So here what type of bond will be there? CH3, CH2, Cn, right? So the bond will be between these two carbons. So these two carbon-carbon bond, that will be stable than Cn. Okay, however, in AgCN is mainly covalent because it's ionic, we said it is ionizing, undergoing ionization. And nitrogen is free to donate electron pair. So in the case of covalent, nitrogen is having a lone pair of electrons. So it is free to donate an electron pair and that will form. So because of that, it is donating an electron pair and joining with this CH3 plus, because CH3Cl when react with the Cn minus, what will happen? This will be first converting into a, it will be reacting with the this NC, right? It will be bonded through NC because the nitrogen consists of a lone pair of electron. Okay, so the lone pair of electron will be bonded with the carbon atom there, and we will get isocyanide as the main product. Okay, now let us do the classification of nucleophilic substitution reaction. We have to learn two different substitution reaction mechanism: the substitution nucleophilic bimolecular and substitution nucleophilic unimolecular. It is called SN2 and SN1. So first we will be discussing substitution nucleophilic bimolecular, that is SN2 mechanism. What does it indicate? It is bimolecular. That is in the rate determining step we can see it is determined the two reactant must have effect on the rate determining step or the slowest step. Okay. And this is a one-step mechanism and it involves highly unstable transition state. Okay, let us see that. Look at this particular reaction. In this particular reaction, if you look, you can see what is happening here. One OH minus is coming very near to this. So it will undergo polarization, right? Then look at this. When OH minus is coming to this, OH minus is going to attach this carbon atom. At the same time, see, this is a very unstable state because all the bonds, how many bonds are there? 1, 2, 3, 4, 5 bonds are there. 5 bonds on carbon atom is not possible. Only 4 bonds are possible on carbon atom. And this will be very highly unstable. And you can see dotted line here and here. That is partially it is joining to the carbon atom, this nucleophile, and partially the leaving group left the carbon atom. Okay. So in the next step, immediately rearrange and you will get OH here and Cl minus here. Now let us see the case what happened. Actually, Cl is going from here, but OH is not coming here. What is the reason? OH will be coming from a side opposite to the leaving group because leaving group is also negative. Okay. So there will be repulsion between the negatively charged leaving group and also OH minus. Because of that, the OH minus, that is the nucleophile, will be coming from a side opposite to the leaving group. So that will result in total inversion of configuration because Cl was here, right? After this, the attaching group will be opposite side of that leaving group. Okay. So it is just like this umbrella. If we are going in a rainy and windy season, if we are moving, we know that our umbrella become like this. Okay. So inversion happened to this umbrella. In the same manner, here inversion happened to the molecule. Okay. So that is in SN2 mechanism. So SN2 mechanism is a single step mechanism. In the single step mechanism, you see both, this is the first step. Both the reactants are involved in the single step mechanism. This is the first step is the slowest step or the rate determining step. So in the first step, both the reactants are involved. That is why the mechanism is bimolecular. And there is an approach of nucleophile. That is why it is called a nucleophilic bimolecular. Okay, and there will be substitution of chlorine by the nucleophile. That is why it is called a substitution. So it is substitution nucleophilic bimolecular or SN2 mechanism. This is the mechanism. Now, one more thing you have to understand here. See, if all the groups are high, this is a methyl group attached to the halogen, only light hydrogen will be there, right? So the nucleophile can easily come. There is no such big repulsion issue there. But if you are introducing the CH3 group instead of hydrogen, what will happen? There will be a steric hindrance. Okay, there will be a repulsion or steric hindrance due to this bulkier group. So the SN2 mechanism is the order of SN2 mechanism is actually primary halide will be highly reactive than secondary and tertiary. What is the reason? In tertiary halide, there are 3 bulkier group. Because of that 3 bulkier group, there will be steric repulsion. Okay, because steric repulsion or steric hindrance should be there. Because of that, the primary halide will be more reacting in SN2 mechanism. Okay. Now, let us see the next case. So this is the inversion of configuration, another example. Br is here, the leaving group, but the incoming group will be attaching from the side opposite to the leaving group. Okay. So we discussed the substitution bimolecular. Now secondly, we are discussing about substitution nucleophilic, that is unimolecular substitution reaction. So what is unimolecular substitution reaction? It is actually a 2-step mechanism. Unimolecular substitution reaction is a 2-step mechanism. Okay, unimolecular means only one of the reactant is there in the rate determining step. Okay. So it mainly involved the formation of a carbocation. Last SN2 mechanism, there was transition state. Here it is a carbocation. The formation of a reaction intermediate will be there. And we need to break this CCl. The first step is what? First we have to see that, then we can come back. Okay. So this is the reaction. When tertiary bromide, when react with OH minus, see this OH Br will leave and OH will come there. So this is an example for SN1 mechanism. And in this mechanism, look at this mechanism. The first step, what is the step? First step involved CH3 thrice CBr. Okay, here the CBr bond has to break. The first step involves the breaking of a bond, and you are getting a positively charged carbocation here. This is the carbocation and Br minus. Since it involves the breaking of a bond, this is the slow step and this is the rate determining step. Okay, so because of that, only the reactant, this reactant will be affecting the rate of the reaction. So that is why it is called a unimolecular mechanism, reaction mechanism. Okay. And in this case, look at this, a carbocation is forming. And this carbocation, since there are 3 bonds, it is actually is having a planar shape. It is planar. So if a carbocation is planar, what will happen? The incoming OH minus group has possibility to attack from both sides. So we will get 50%, there are 50% chance for attacking from this side and 50% chance for attacking from this side because it is planar. Okay, so we will get 50% product that retain its configuration, that wherever the bromine is there we will get OH group, and 50% will get with inversion of configuration. Understand? So that's all. Now, next thing is, if you think about the ease of formation of or the order of reactivity, we can see that in the case of SN1 mechanism, tertiary is better. Tertiary is more reactive than secondary and primary. So we can say that secondary will do both SN1 and SN2 mechanism, but primary will do only SN2 mechanism. Secondary, both SN1 and SN2 mechanism. This came in your paper. And tertiary will do SN2 mechanism. Because, what is the reason? Because there is a formation of carbocation in the steps, right? If you take this particular step, you can see that there is formation of a carbocation. And we have learned in hyperconjugation and all the formation, the stability of carbocation already we discussed. There are different type of carbocation. This is CH3, CH2 plus. Okay, this is primary carbocation because this carbon atom is attached with the one alkyl group. Okay, now this is CH3, CH3, C. Plus H, secondary carbocation, because the carbon containing plus, okay, positive charge that is attached with the 2 CH3 group. Now tertiary is also there, CH3, CH3, CH3. So the carbon bearing positive charge will be attaching with the 3 CH3 group. Okay. So the more resonance structure or the dispersion of positive charge will be more in this, because 3 plus 3 plus 3, 9 structures are possible. So 9 atom, this positive charge can disperse. So because of that, this is more stable. Okay, more stable carbocation, because more resonance, if there is more resonance structure, more stability will be. And next is this, and next is this. So the SN1 mechanism depend upon the stability of carbocation. So stability of tertiary carbocation is more than secondary, so in turn is more than primary. Because of that, tertiary carbocation, the order of reactivity will be like this. If it is tertiary alkyl halide, that will be more prone to react using SN2 mechanism. Sorry, SN1 mechanism. Okay, SN1 mechanism. Now, if you see the order, we can see that order also. This is the order. Okay, SN2 reaction and SN1 reaction. So tertiary halide in SN2 reaction, Who is more reactive? Primary halide. If you take SN1 mechanism, tertiary halide is better. And the secondary halide will react using SN2 or a SN1 mechanism. Now, allylic and benzyl halide show high reactivity. What is the reason? If you look at allylic halide, you can see that the carbocation, only carbocation is drawn here. If you take any allylic haloalkane, look at the CH2, CH, CH2Cl. When you leave the Cl, you will get a positive charge here. And what will happen to this positive charge? That will undergo resonance. This bond will come here and the positive charge will go here. So the next structure will be CH2 plus CH double bond CH2. Understand? So it will undergo resonance. Two resonance structures are there. So this structure, the carbocation formed is stabilized because of the resonance. So it will show SN1 mechanism. Understand? And here also, if you look at this one, CH2Cl, when you leave Cl, it become positive charge. When it is become positive charge, what will happen? Resonance happen. From here to here, the electron will move and the positive charge will spread all over, right? So because of that, it is getting more resonance structure. It is resonance stabilized, the intermediate carbocation. So it is also having high reactivity, okay, towards SN1 mechanism. So if there are same alkyl group, this is applicable for both SN1 and SN2 mechanism. Suppose we have the same alkyl group, okay, RH. So what will happen? Same alkyl group is there, but only the halogen atom is changing. So the order of reactivity is this will be more reactive because already we discussed it is having a long, this is having Ci bond, right? The Ci bond is long. The bond length is longer here than the corresponding RBr, RCl, and RF because the size of iodine atom is more than Br, Cl, and F. Understand? So it will be very, since its bond length is more, easily we can dissociate it. Okay, easily it will undergo dissociation. That is the reason why Ri is more reactive than RBr, which in turn is more reactive than RCl and then RF. Okay, because it is very small, the reactivity is very less because the bond length is very short. So you need to apply much energy to break this bond, CCF bond. Okay. So now we can see, already I discussed that. Now we can see the difference between SN1 and SN2 mechanism. Okay, so actually who will do SN1 mechanism? Tertiary alkyl halide, and SN2 mechanism primary alkyl halide will do. And the number of steps involved in SN2 mechanism is SN1 is opposite. You see, if it is SN1, two-step mechanism. If it is SN2, one-step mechanism. Okay, so SN1 means two-step formation of carbocation is there. So the transition state or intermediate state, which is forming, we are getting a carbocation intermediate here, and in SN2 mechanism, we are getting a highly unstable transition state. Okay, and because there are 5 bonds to the carbon atom, that is why it is highly unstable. We cannot separate such a transition state anywhere. The solvent we are using for SN1 mechanism is polar protic solvent like H2O, those which contain hydrogen atom which is attached to a highly electronegative oxygen, like H2O. Water is an example. Okay. So in SN2 mechanism, we are polar aprotic. The hydrogen is not necessary. Hydrogen, which is attached to a highly electronegative atom, is not necessary. Acetone we can use here as a solvent. Okay, we are not discussing the solvent here during the reaction. So polar aprotic is okay here, but polar protic is needed here. Okay, and the type of bond fission, both of them will undergo heterolytic bond fission. Okay, you have learned heterolytic and homolytic for bond fission. In homolytic bond fission, we are getting free radicals. Since here we are getting positively and negatively charged ion, the bond fission here is heterolytic and in the both case. Okay, so that's all about SN1 and SN2 mechanism. Okay, thank you. Thanks for today's class. Now we will discuss next part in next class.